using the diagram in your booklet as to how the loop of Henle maintains the reabsorption of water back into the blood. Now, just to give you an idea about where you are in relation to the nephron, this obviously is the loop of Henle here, and we are in the medulla of the kidney, and this is the descending limb of the loop, and this is the ascending limb of the loop. Up here is the distal convoluted tubule, this is the collecting duct, and then up here, this is just the end of the proximal convoluted tubule, which will carry on up here off the page somewhere, and then obviously the Bowman's capsule is around there. Now, just a few things to note about this. So the first thing is the name given to the space between the different parts of these areas in the nephron is the interstitial space, and in the interstitial space will be tissue fluid, and that's important because that's where the water will be moved into before it enters the blood. The other thing that we really need to be aware of that's not shown on the diagram is the nephron will be wrapped in an extensive capillary network, because that will then take the water molecules away from the nephron. So although it's not on this diagram, just to simplify it, that will actually happen. So you just got to be aware that this will have an extensive network of capillaries around it, just to maintain the osmotic or water potential gradient. Okay, so let's have a look at what is happening. Now, the first thing to remember, the ascending limb has a thick wall impermeable to water molecules, and that's where we'll begin. So we always begin, when we talk about the role of the loop of Henle, at the ascending limb. Okay, so number one there. Now, what will happen first is sodium ions will be actively transported out of the ascending limb and into the interstitial space. Okay, and the interstitial space between the ascending and descending limbs, and also the interstitial space between the ascending limb and the collecting duct. So now we have a higher concentration of sodium ions in the interstitial space. This will then lower the water potential in the interstitial space. We know that the ascending limb is impermeable to water, so water would normally move out by osmosis. However, it's impermeable, but the descending limb is permeable to water molecules. So now what happens is at number 3, water molecules diffuse out of the descending limb by osmosis. Now, when the water molecules have diffused out and entered the interstitial space, into the tissue fluid, there is now a higher water potential in the tissue fluid than in the capillaries. So the capillaries then will take that blood away because it'll enter the capillary by osmosis. Okay, so you can't see that on the diagram, but that's what will happen. Now, as we move down the descending limb, you can see that the water potential, or the concentration of the filtrate, gets more and more concentrated, and it reaches its most concentrated point at the bottom of the descending limb. So this down here is where the filtrate, the water potential of the filtrate, is at its very, very lowest, because there's not much water here, but we've got lots and lots of ions and other molecules inside the filtrate. Now, at the base of the ascending limb, which is here, sodium ions diffuse out of the ascending limb. So rather than being actively transported out, sodium ions diffuse out here. Okay? And when the sodium ions diffuse out into the interstitial space, what that will mean, if you look now at the numbers, relative now in the filtrate, there are now less ions in the filtrate up here, because the ions are either actively transported out up here or diffuse out down here. So relative to water molecules, now the filtrate actually is getting a higher water potential, just because now, relative, there are less ions. But if you look now, what you've now got, because you've now got loads and loads of ions in the interstitial space, and the ion concentration gets progressively higher as you go further down into the base of the loop of Henle. That means that although by this point where the filtrate enters the collecting duct, although there'll be a very, very, very few water molecules in there, the water potential in the collecting duct is always higher than the water potential in the tissue fluid or the interstitial space, because there's just so many ions in there. So therefore water will always move out of the collecting duct by osmosis, because remember, it's all relative. Although there isn't really a high water potential in the filtrate in the collecting duct by this point, because a lot of it's already been removed by osmosis earlier on, relative to the concentration or water potential gradient of the interstitial space, there is still more water molecules in there, so they will move that by osmosis. Once they've moved out of the collecting duct, they'll move into the capillary and be taken away from the nephron. Now, this is called a countercurrent multiplier, and the reason is because this exists all the way through the nephron itself, and this is why it's really efficient. Now, if you remember how the countercurrent works, it means that different fluids flow in opposite directions to each other, and that always causes the movement of a certain molecule from one and into the other. And you can see the filtrate flows downwards here, which causes the water molecules to move out. Flowing up there, the sodium ions move out, and then it flows down again, which causes more water molecules to move out. So this is the countercurrent multiplier, and it exists for the whole entire length of the nephron. And at no point do the limbs, so i.e. the descending limb, the ascending limb, and the collecting duct, flow parallel to one another, which always means the water always will diffuse out of the nephron by osmosis, and it will always then diffuse into the blood capillaries by osmosis again. And that's because we have that countercurrent multiplier.